Hey guys, this Houdini project file is available on GoRoad. You can watch the full tutorial for free here on YouTube and grab the complete file to boost your studies. The link is in the description. Let's create our pool of grains right now. Let's move this here. Create another geometry node. Rename this to gel, pool, waves. Change the color to purple. Let's dive inside. Create a box. Move it to camera 2. Let's create a box of 17 in X and Z. Let's see in the camera 1 if the box is occupy all the camera. The height of the box is around 0.22. Let's create a match size. Minimum in white. And create a Vellum Grains. Vellum configured grains. Here, create points from volume. Enable jutter scale to avoid the alignment of the grains. Enable adjust radius to avoid overlap. And change particle scale around 0.035. We have around 160 million polygons. Let's create a Vellum solver. Move down there. Connect here, connect here. Connect the third input. Change here to minimal grains. Enable substeps of 5. Constraint iterations don't need to high value, like 10 is enough. Enable the ground position. Disable the wind. No velocity damping. Ground static scale should be around 0.5. And ground dynamic scale around 0.5 as well. Let's create our file cache. Rename the cache to cache grains scene. And we can delete some attributes here to avoid the cache unnecessary attributes. Delete everything except GL sphere points for visualization. And okay, that's it. Let's delete the group. We don't need any group in the cache. Let's save the cache and see what has happened. That's the result of the caching. You can see the grains sliding on the ground. We need to stop that. To stop the grains sliding on the ground, we need to select some fill points, all the border points here, and disable from the Vellum simulation. To do that, we need to create a bound. From here, the match size. lower padding of minus 0.1, copy parameter, paste relative reference, paste relative reference here, upper padding X and Z, and here around 0.2 and 0.2 as well in the Y for lower and upper padding. Let's disconnect here to organize. Create a group from here. Name this to group. Inside we need to keep the outside group disabled from the simulation and inside group enable in the simulation. Move this down here. This is the inside group. Keeping boundary regions, boundary object, primitive points. Create a little Vex script here. Rename to Vex mass outside. To make the points outside, these edge points here, disabled from the simulation, we should set the script here. Mass is equal 0. If the mass equals 0, means that there is no interaction from these particles inside the simulation. Group inside with an explanation character. Everything outside, every border here is disabled from the simulation and inside is enabled from the simulation. Let's create a divide. Connect here from the bound. Disable convex polygons, enable breaker polygons, copy parameter, paste a relative reference to Y and Z. And here 0.05, 04. Okay, create attribute noise. In position, amplitude a little bit small, like 0.15. Element size around 0.2. And create a transform. Change the name to lift. Lift just a little bit, like 0.2. And create a group here. Connect the lift to the second input. Rename the group to group, top, point noise. We are going to subtract from these points a little bit noise points from the top to make it more interesting surface at the top. Instead of just flat, we are going to have some disturbance from the grains at the top. Change here to points in the group, disable the base group, keep the boundary regions enabled and change to object. Now you can create a delete, just to delete the top points. Okay, move more upside a little bit. Like this is enough. Delete top points. noise. Change to points and select this group here. Group top points noise. Let's see if the selection is working. Yes, with selection, without the selection. Let's connect this here to the first input and create another delete attribute to delete every attribute and create the constraint here. Let's create our collider just to see with the colliding joystick animation. Object merge. Create a checkpoint. Rename this to ref joystick collider. Let's find the collider. Geo joystick anim, alt joystick anim, okay? Actually, we need to find the collider. Geo joystick collider, alt joystick collider anim. Create a VDB collider. Change here to animate the rigid. Voxel size should be 0.01. Disable the friction and connect to the third input of the solver. Rename this Vellum solver to grain solver. And make a cache and see what has happened. That's the result of our simulation. Our simulation is working. Right now we need to create some driving force, velocity field to control how make the particles explode, how make the particles following the shape with the colors, how create a vortex force to move the particles first from the beginning here and make the shockwave, final shockwave. Let's go inside the grain solvers. Create here a pop limit, pop speed limit, change the maximum speed to 4. Here, let's adjust which attributes we need to delete and which attributes we need to keep. Actually, we need to keep to the ID. We don't have ID, we need to create these IDs. We don't have any ID, we need to create. Let's create an ID here. Vex ID. at ID equals @pitina. Because in the simulation of the Vellum Grains simulations, there's no deletion of the particles. The particles remains the same count throughout the simulation. There's no need for ID. Actually, you just need to compute the velocity using trail, compute velocity. Let's randomize the orient attribute. Actually, you can move the compute velocity here after the cache. We need to randomize the orientation of the points, orient, dimensions 4, and direction orientation. Create a checkpoint here. Out, pull, simulation. Color black. Let's make the cache again. If you want to instantiate the symbols for the grains just for visualization here, because when you're going to render this, the instances will not be creating SOP level. The instances will be creating Solaris level. But for viewport preview, we can create the instance here. Let's create a copy to points. Let's import our object here, our symbols. Here you can select geo symbols, out symbols, but here we need to see all the symbols at the same place. Then we need to go here, load the symbol by symbol, out circle, merge, connect here, triangle, cross, and the square. All the symbols are here. Before connecting these geometries, the symbols to the pack, to the copy to point here, enable pack and instance to avoid the slowdown of the instance. Let's see what is happening. That's our geometry, but we need to fix some stuff here. We need to adjust the scale of the symbols and just copy one different symbol for each p-scale, each randomized p-scale. To create that, let's first adjust the scale. Around 0.2. I think is okay. And you need to keep each symbol for each particle and randomize this. We can do that. Create a pointer angle here. Create a vector attribute. Random shape, random symbol. We can use the name attribute for each symbol and create a respective name attributes at the point as well. Create here at name equals circle, floaty random equals random for each ptnum, and decide based on these random attributes if rand let's convert this to int. Integer is much better. Int rand times 4. If rand equals 0, should be a circle. Copy this line more 3 times. If rand equals 1, should be a square. Equals rand equals 2, should be a cross. Equals rand equals 4 for 3. The name should be triangle. Let's see if the name is working. Circle, cross, square, triangle. Okay. Here in the copy to points, we can enable the piece name to change the variation for each symbol for each particles. Now that's working. We can have each particle assigned for each shape. You can see the simulation with the symbols. Let's see the camera 2. Let's move the frame a little bit. Actually, can zoom in a little bit and create a play blast. That's the result of our first test. We can see here there's a lot of particles. The camera space is correctly populated with the grains, but for the test simulations we don't need all the particles here. We can change the bounding box size of the grains to a much smaller size. In the next step we are going to create the vortex force to move these particles away from the joystick. That's the first movement behavior that we need. The vortex force to move particles away from the joystick. Let's see in the other camera here. The joystick is animating and the particles have a vortex force to separate the particles from the joystick and release them on the pool of the grains. Before creating this vortex behavior key from the particles, we are going to analyze which effects we are going to use in the entire shot. Here we have the Shockwave, which separates the particles from the joystick. The next effect is this line formation here, like line grab, and the line is release. We are calling the line is grab and line is release. And the final Shockwave. There's 4 steps for these effects to organize in our Vellum simulation. We are calling the vortex, line is grab, line is release, and Shockwave. Let's organize that inside the grain solver. Here inside the solver, let's create a checkpoint, each one for its effect. This is ref vortex. Ctrl C, Ctrl V. Ref lines. Lines grab. Ctrl C, Ctrl V. Line is release. And the last one, Shockwave. Let's merge all this reference. Plug here before the pop speed limit. And let's create a little setup here. Create enable solver, which define which frame these effects will be applied to the simulation. Let's create a pop, advect by volumes because we are going to construct the vortex field in SOPs. Connect here. And let's create the vortex. Let's hide these nodes here. Create a geometry node, rename it to gel, velocity field. Change the color to purple. Go here. Organize in a box. Rename to pool. Let's dive inside. Create object merge. Let's pick up our collider static here. Geo collider static. Okay. Let's create a normal. Because you are going to use the normal to create a vortex field in the points. Let's create a VOP, point VOP. Inside here we are going to create the vortex. Let's rename this to VOP. Vortex. It's a pretty simple setup inside. We need to normalize the normals here. Create a constant here at up vector. Vector. Rename to up. Up vector should be 0, 1, and 0. Create a cross product from the normalized vector for the surface to the up vector. Let's visualize that. Here just the normals from the surface. Let's see how the normalized version, the normals will be changed by this cross product here. Let's apply again to the normals and see what is happening. That's our vortex field, which is each normal is aligned like a twist here for all curved angles from the joystick. But we need to apply this to the velocity instead of normals. Instead of normals, we need to apply this to the velocity here. Just that. Let's scatter some points here. Around 10,000 points. Create an attribute create here. Name it P scale. The value should be 0.1. Let's see this in velocity instead of normals. Enable the velocity. Let's copy our animation transforming. Just to move the animated velocity in the same time with the original joystick. Let's copy that. Here in joystick and in, copy this node, Ctrl C, go back to the velocity field and apply here. We have the same animation from the joystick applied to the velocity field. Now you can use a clip just to clip the points below the ground. We don't need any points below the ground because there are no grains in below the ground. Clip in Y direction. like this. And create a volume rasterize attributes to convert the velocity points to the VDB. Velocity, okay. The resolution is okay. You can increase a little bit of the resolution. And create a checkpoint. Out Vortex field. Just that. Before applying this to the simulation, we need to invert the velocity here, because the velocity looks okay, but is inverted. If you are going to use this velocity inside the grains, the particles will shoot up in the inverted direction, like this direction. We need to make the particles shoot in this direction here. It's pretty simple. Create a angle, pointer angle, change this to Vex, invert Vel. Just single line here at V equals multiply by -1, just to invert. That's it. We invert the velocity. Let's see what is happening in the simulation. Here the pop advect by volumes. Just grab the velocity vortex field here. Out vortex field. Update force okay. Treat as wing disable. Force scale should be 50. We are going to use some Vex functions here to adapt to the vortex field, but let's see the simulation before any change here. Here you don't have any applied force scale. Let's see what is happening. And adjust the pop advect by volumes with some Vex expression here. Enable use of Vex. Create a little script here. Float amp. Scale. Amp force equals. We need to apply force. For example here, look at the side view. We need to apply high force in vortex force in the up and low vortex force in the bottom here. We don't need too many forces here, but here we need to be strong. The force at the top needs to be super strong. Create a force based on the Y position. CH-amp. Amp Y. A fit at P.Y. by some position here. Let's create two variables here, minimum Y, maximum Y. Float Y min Y equals CHF min Y. Copy this line, maximum Y, max Y. Change it here to min Y, max Y. 0 and 1. That's the script. Apply here. Minimum Y should be 0.2. Maximum Y by 1. This ramp Y should be curved like this. Baseline here, this way. force scale 50, force scale times equal, another variable here, estimate amp force, force multiply. Actually, let's change it here to amp force and change this variable here to just to amp times amp. We are going to apply maximum force at the top, lower force at the bottom, just used by expression here to multiply this force scale. But this force scale will be animated. From the first frame, this should be 0. Few frames later, like 10, should be 1. And that's it. Let's see the curve. Let's see if it's working. Let's create the cache. Now it's working. We need to fix here, inside the Vellum Grains, the name of the field should be V instead of Vel. Now let's colorize this with an appropriate color, like in the render. For example, the high velocity particles I color to white. Let's do that. We create here a pop wrangle, rename to Vortex, color by speed. Change the color to purple. We need to create a little script here. Based on the speed of each particle, we are going to apply some color. The script is float speed equals length of velocity vector color equals CHV, CHRamp, ramp color by rand of PT_num. Int frame limit should be the maximum frame to calculate to change the color of the speed particles, the fast speed particles. Frame limit. Frame limit is CHI. Frame limit. Okay. Let's change it here to color. Color ramp. Instead of float, just color. Actually, you need to change here. Blue. Blue here. White here. You can change the value, the colors later, for example. Let's change to white and see what has happened. To white and red. Like this. And change the color based on the speed. If speed greater than CHF, mean speed should be an attribute, a variable. At cd.r x equals lerp Add cd.x by 1 and 0.3. Else, just copy this color here, cdx, lerp from cdx 0, 0.3. These are going to change the color based on the velocity, the speed. Frame limit should be 95. Mean speed should be 0.5. Let's see what is happening if it's working. Actually, we need to keep the color. Let's save. Here we can see like a mask. We can change this the cyan color later for which color we want. The high velocity part is already white. Let's change this in make a process color here, just to change the cyan color to red, for example. Create a pointer angle. Name this to Vex. Color post process. And create a little script here. Add cd.b times 0.5. Float luminance equals luminance from cd. At cd equals chramp ramp color from luminance. Change here to color. Let's change to red and white. Now you can see that it's working. Modify the high speed colors. The high speed particles to white. The static particles still in red. You can make a little variation here in the red colors. Just simple. You can create a VOP, point VOP, connect here, rename to VOP, color variation. Let's dive inside. Let's create a random from ptnum. Create a feature range. From values 0 to 1, from minus 0.05 to 0.05. Create a color correction node. Connect this value to the shift. Original color here. And output to the color. Let's see if it's working. Yeah, the red color have a little bit variation. I think it's too strong. We need to reduce that. Here we can copy this value or create a parameter here. Promote the parameter. Promote parameter. You can reduce here to 0.02, 0.02. Okay. With variation, just red with variation. Okay. Actually, if you want to blend this, we don't need all the particles should be color variant. We can create a randomize if the PSK, the randomized particles should be applied this color variation or not. We can use a Vex, another point here, connect this direct here and develop in the second input. Rename this to Vex blend color. Grab a little the color from the second input, vector, color equals 0.1. This is color for each patina. If range at patina less than some variables, bias at CD equals color. The bias should be a very small value like 0.2. Just few particles have different colors here. It's enough. Let's see the result from the camera with the joystick. That's the result of the simulation with the Vortex. Here, at the beginning you can see there's blend colors because the particles is falling down at the first frames to the ground, and later the particles is still for later to apply the speed base, the color based on the speed. At the first frame here, we need to apply a pre-roll in the simulation like 10 or 20 frames to fix that beginning here. The next force field we are going to apply right now should be the Shockwave, because Shockwave is much simpler than the lines. The lines are a little bit complicated, and let's create this effect at the final. Right now you're going to create this Shockwave. Let's go inside the geo velocity field. Create here a checkpoint for the Shockwave. Out Shockwave lines. Color black. Let's import our joystick, object merge. We need to import the animated version. The joystick, anim here. Let's create a time shift for the first frame. Let's convert this to polygons. And extract a silhouette using labs extract silhouette to the Y. Let's create a poly expand to shrink a little bit the outline. Disable recompute point normals, and offset is enable like 0.3. Disable output outside, we just need the inside. Convert this line. Because this is a geometry, you need to convert this to line. Create a polyframe. Change here to bitangent name to normals. Let's see. That's the Shockwave direction. Let's move a little bit. Disable recompute to normals. Let's resample this. In the length 005. Let's move this to align it to the ground because it's below the ground. Zero Y. Just make the Y scale 0. Okay. Let's give a little bit noise for each normal using a VOP. Rename this to VOP. Noise normals. Let's dive inside. Create a turbulence noise using position for the noise. Promote all other two parameters. Create input parameters. Let's fit the result of the turbulence. Like minus 0.7 to 0.7. Destination should be 2 and 6.6. Let's create ABS to make this value absolute, to avoid invert the direction of the shockwave, and multiply that with the normals. Multiply the normals by this ABS and apply back to the normals. That should be amplified by the noise. Let's adjust the noise here a little bit. Change to the simplex noise. Increase the frequency like 30 in our 3 axis. Amplitude by 7. And change the roughness a little bit, like 0.3. Reduce the turbulence by 3. And that's it. This is our shockwave direction. Let's create another VOP. Point VOP. Rename this to VOP. Noise P. Let's dive inside. Let's create another turbulence noise here. Connect the position. Create spare parameters. Let's fit this noise. Like minus 0.3 to 0.4. Negative here. Let's normalize our normals. And multiply the normals with the fitted. And add this to the position. Position. Add the multiplied normals and apply back to the position. Like this. Let's change the noise frequency here, like 4. Change to sparse convolution. Amplitude should be decreased by like 0.6. And adjust the roughness a little bit more chaotic. Create a angle. We are going to make another adjustment in the normals to make this speed, like a speed. Rename this to Vex, Random, Vellum Intensity. Let's connect this to the checkpoint. Let's create a variable here to be controlled inside the grain simulation. At max speed equals length from normals. That's it. The length, max speed should be the length of the normals. Now let's dive inside the simulation. We know the name, Shockwave lines. Let's go to the simulation here. Let's dive inside the grains. Grain solver. We are going to change here, the Shockwave. For that we need to create a pop angle. Connect here, change the color to purple, change the name, Vex Shockwave. The activation for the Shockwave should be between the frame 150 to 155. $FF equals greater than 150 and $FF less or greater or equal than 155. This should be activating just in small range. From this to this, like 5 frames of the Shockwave. Let's load here the lines, the Shockwave lines. Let's find velocity field, Shockwave lines. Let's create a script here. We need to grab each position from the Shockwave lines, the normals. Int near pt equal near point 0 for position. Let's grab the position of the near point. Equals point 0 position for each near pt. Let's fix the name here. Let's grab the direction of the Shockwave vector there equals normalized from position and near position. Float distance is the distance from the position of the current point to the normalized point at the Shockwave line. Equals distance at P from near pos. We need to apply some noise here. Let's create noise in Vex. Let's give some space. Float frequency equals CHF frequency noise, some amplitude equals CHF amp noise, and create a noise here. Float noise equals S noise. From there, times frequency times amp. Noise equals CHA ramp to adapt the noise in the ramp curve. Ramp noise, the value of noise times 10 to amplify the noise scale, and clamp the noise value to avoid the strong or the smallest noise. equals clamp noise from 0 to 5 maximum. Let's adjust our ramp here. You just need to change here to B-spline, increase a little bit here. For the frame we need fast apply shockwave. Now, for apply the force to each particles, we need to apply to check the distance. If distant less than noise, at force plus equals direction times another variable here, CHF, amp force, and give a little up velocity at force plus equals CHAV for up vector, up there. Let's see if this value, up direction should be 0, 1, 0, amp force should be 5, noise frequency should be 20, and noise amplitude should be 1. Now you want to apply some mass information for each particle to make the particles shockwave moving in different speed. For this, we create a mass equals 51 to vary the speed and vary the mass for each particles affected by the velocity. Noise CHF mean mass, CHF max mass. And randomize a little bit, increase the force, the mass, by some random value. If rand of PT9 less than 0.05, apply a different mass here, equals 51 rand from PT9 from 1 to 10. Increase the mass for a small count of particles. Let's change the min mass and max mass. Min mass should be 0.03 and max mass should be 0.1. Let's create another. Let's copy the color by speed. Ctrl C, Ctrl V. Rename this to Shockwave color by speed. And adjust some script here. At the Z, instead of using CDX, we are going to use CDZ. Min speed should be 2. And that's it. Let's see the simulation. Here we just need to fix here. I forgot to close this line. Now I think it's working. Let's check. That's the result of the Shockwave final. I fixed the start here, giving a 20 frames per roll in the simulation. I changed this here to give it a 20 frames per roll here, minus 20 start frame. The next behavior we are going to create right now is this lines formations here. You can see that each line is forming a few frames after another. And when they start, the lines start to become white, There's an attraction here for the points near to the lines to attract to the invisible lines at the middle of the region here. For example, there's a line in the middle of the white region, another line here, and the lines are activated and the grains are start to attract to the lines. You can see here in another camera, attraction for the grains to the invisible line. At the final here, the final look, you can see when the line is activated, there's attracted the particles to the lines and the lines starts to accumulate on each other. That's the effects we're going to construct right now. First, let's create a geometry node to create the silhouette of the joystick. Rename this to gel silhouette. Change the color, put inside this container here, and let's dive inside. Import our joystick here, the original asset. Joystick asset. Okay. Without any animation. Convert this to polygons. Extract the silhouette using extract silhouette labs. Change it here to Y position. Let's create a group here. Rename it to group bottom points. Change here to points, enable the bounding box region, move the bounding box down here, let's create a transform to move these points up, group bottom points over like 0.2, it's okay, it's value. Let's create a smooth to smooth these edges here. Filter quality to 1, constraint boundary to none. Okay. Create a for each by number. Connect here. We are going to interact around 4 times. Create a poly expand. Connect here. And here we are going to create some expression here, the offset. Disable the offset inside. And here put an expression 1.05 times the tail. Actually, you need to rename this meta 1.05 times the tail of meta iteration comma 0. We create 4 offsets for the silhouette. Let's resample. Resample by 0.5, 0.05, and let's create a smooth. Constrain boundary to none. Create a checkpoint. Alt silhouette. Lines. Change to black color. Let's go inside the velocity field. Let's create object merge and grab the silhouette lines that are created. Silhouette, out silhouette lines. We convert this to lines. Convert line. Connect the path. Create a measure. Change here to perimeter. And let this attribute name perimeter. Sort. We are going to sort each primitive by the perimeter. By attribute. Perimeter. Here we can see that the Y position is above 0. We need to translate that to 0 absolute. Transform 0 in Y. And this case should be 0 here. Okay. Let's delete all the attributes. And delete all the groups. White card here. Create a checkpoint. Alt, joystick, multi-lines. Connect here. And we are going to create some animation here. Create a Vex, pointer angle. Rename this to Vex, anim. Grab state. We are going to animate a variable here to define when the particles around the line should be grabbed by the line and make this formation here. We change both the color and both the position. That's the first part, the grab. And the release with force we are going to make later. The script here should be int start frame start equals CHA start frame int frame interval equals CHA frame interval. In start frame, that's the beginning of the first line when they be activated. The frame interval should be the frame when the next line will be start after this line was started. At grab state equals 0. If at frame greater equals frame start plus frame interval times at prenum. At grab state equals 1. Change here to primitive. To see how these grab states are working for each primitive, we can promote this attribute promote, from primitive, grab state to points, promotion method should be maximum. Let's fill the start frame and the frame interval here. Start frame should be 85. Frame interval should be 7. 7 frames by each line activated. You can see it here by the color, for example. Color. Ramp from attribute, grab state. The lines are activated at the start frame 85 with an offset of 7 frames. You can disable the color here. We are going to use this joystick multi-lines inside the grain solver. Inside the grain solver, let's create a wrangle. Connect here, change the color, rename to Vex lines, grab. Let's load here in the inputs, SOP, load the line. Alt joystick multi-lines, accept. The start should be in frame 85. $FF. Grade equals then 85. And finish at $FF. Less equal than frame 135. Let's create a little script here, just a few lines of script to control the grabs with the lines. First, we need to create a vector, particle position equals at P. Consider all the positions in the y equals 0, int near point. Let's grab the shockwave line. Let's grab the outline, the multi-lines here to see the distance. Near point 0, particle pose, near pt equals, let's give some space here, vector pose equals point 0 position from this pt none here, the near point. Vector dir equals normalize the pose minus particle pose. Float dist equals distance to the particle pose and pose. Here you're going to grab the grab state variable. Grab state equals point grab state near point, near pt. Now we're going to check some variables here. If distance less than CHF. Max distance. E, we have a grab state activated. We are going to grab the near particles from each line and do some stuff here. Else, we are going to do other stuff. Let's create a float. Bias force equals chramp. Ramp. Let's give you more space here. Fit. Distance 0 and max distance. You are going to create a fit, a ramp for the distance. Max distance 1 to 0. Float. Bias color equals chramp. Bias color. Fit distance 0 to max distance. Copy this. 0 to 1. At cd.ey equals lerp. The current color at cd.y 1. Bias color times 0.7. Let's create some randomization here. If rand the ptnum greater than CHF, let's save. Threshold return. Another if here. If at p.y less than chf minimum y, min y, return as well, because we don't need to grab the bottom lines near to the ground. Return. And apply the force at force plus equals direction times ch force times bias force. Elf, just keep the same color at cd.y equals 0. Let's fill the variables here, the values. Max distance is 0.35. Min y is 0.02. Threshold should be 0.8. Force should be animated parameter here. At the frame 85, the force should be 0. Frame 91, the force should be 2. Let's see if the setup is working. Let's cache. Here we have some error here in the script. We need to close this, fix this line too. We need to remove this. Let's cache again. We forgot to adjust the ramp values here. The first ramp should be inverted. The second ramp should be lining up like this. And down like this. Let's save again. Let's adjust the ramp color here, just to see the line grabs. We need to move the white to here and the red here. Let's see if the simulation from the beginning is working. The particles from the beginning are not becoming white. We need to fix that. But the line grab is working. Actually is inverted because all the ground is red. Let's invert this. Here is red, here is white. Let's see from the beginning. We need to fix the transition of color. Let's do that. The Shockwave is working. Shockwave is working as well. But we need to fix the transitions from the beginning to the line grab. Before creating the cache, we need to make some adjustments here. We need to create a black color here before the grains. And here we disable this Vex color process here and create another blend colors. That's the script here. Because if you create the cache with the black color at the first, that should be the result of the simulation. The first stage is red and purple. The second stage of the lines is green. And the final stage should be blue, the Shockwave. And here, these nodes will blend the colors on a single effect. Let's see the result. Let's make a flipbook. That's the result of our simulation. Now here, we need to make the lines release before the Shockwave. Like in the final render here, we have done the lines, and now we need to make the lines release to blend all the lines just to the color original, which is red in this case. That's the final stage of the simulation. The line is released before the rendering. Let's work on that. Here inside the grain solvers, let's dive inside. We don't need this ref lines release. We can make it just here and rename this just the ref lines. Okay, and create another wrangle here. Poppy wrangle, rename it to Vex. Line is release. Change the color. And let's write our Vex code here. The activation of the lines release should be in different frames should be in a different frame than the line grab. The activation starts at $FF frame 135-36, and the finish is at frame 166-56. The release starts after the end of the lines grab, and release takes around 20 frames. Let's write our script. For the binding here, we are going to use the same binding for the grab. That's the same path here. Just paste the same path. Let's give some space in the script. Vector P, particle pose equals P. Particle pose in Y should be 0. Vector pose equals min pose 0. Particle pose vector direction equals normalize the vector from the position to the particle position. Float dist equals distance from particle position to the position. If this is less than CHF, max distance. If range from PT9 less than some parameters, so the parameter should be a threshold. Float bias force. Let's give some space here. Bias force equals ch ramp fit from dist 0 to max distance. By 0. At force, we increase the force plus equals minus direction, because the direction right now is opposite direction. The grab should be making one direction and the release in an inverted direction. Times CHF force times bias force times fit from range de PT9 0.5 do 2. Add the up vector here plus equal set 0, 0.5 in Y 0 times CH force. Here we apply the force. For inverted the grab. And here we apply the colors. Back to the original, which in this case should be red. Int start frame equals 70. Int random frame blend color equals start frame plus some value here. Some value randomized from the PT9. From 0 to 10. If at frame greater than this variable here, random frame blend color. We are going to set the color. cd.y equals lerp from the current color cd.y to the 0 at the speed 0.3. Let's save and cache and see if it's working. Here we need to fix the script here. The line 14 should be fit 01. Let's save the cache again. Here we forgot to populate the parameters. Let's do that. And adjust the curve, the maximum distance and threshold and the force. Animate the force. The threshold should be 0.4. Max, this should be the same from the lines grab. Copy parameters. Paste the relative reference here. The ramp should be inverted. And the force should be animated. Here at frame 135. 36 should be scale 10. A few frames later, like 140, should be 0 at the force. But it's linear. Instead of curve, should be linear. Maximum force for around 5 frames. Okay, let's cache again. That's the final version of our simulation with all the 4 steps. The vortex at the beginning, line grab, line is release, and the final shockwave.